Hi, hi all. I'm Rohan. Today I thought I'd talk about some randomized algorithms. Can you all see my screen?
Yes, it's
Yeah.
visible.
Okay, nice. It would be nice if you all have your videos on, or like some of you have your videos on. It's always more fun that way. Uh, Please feel free to speak up if you have any questions. Please ask doubts, especially if you're unfamiliar with some amount of probability or some amount of having seen algorithms before, this might be a bit confusing. So please do ask questions. Uh, you can put things in the chat. I'll try to be on top of the chat. Uh, I might miss it, so it would be nice if like I miss something. If somebody else is willing to speak up, they speak up. If you don't feel comfortable speaking up or putting messages commonly, you should feel free to use anonymous messages to me. That is completely fine. I do have the chat open in a different tab. It's just like it should be fine. Um, Good. Any questions before we start? Okay. So a quick show of hands. Who all have seen some algorithms before? Like know what an algorithm is. Let's start from there. Some people are clapping at the idea of an algorithm. That's great. Very excited. Okay, so some people have seen know what an algorithm is. So many people don't have not seen what an algorithm is. So, okay, good. So unfortunately for you, I'm going to throw you into the deep end. I'm going to tell you what an algorithm is and then directly show you algorithms which use randomness. Okay, so good. What is an algorithm? Sequence of steps to get a desired output. Sequence of instructions, you can say, that you do, that you run on some input and you get some desired output. That's an algorithm. Just a very generic, simple definition. Good. So what are we going to see today? The plan is to see two algorithms at the very least that use randomness in very interesting ways. So the first algorithm we'll see is called Kargar's min-cut algorithm. This is one of my absolute favorite algorithms. It's like still crazy to me that this works. The second one we'll see is primality testing. How to check if a number is a prime. Miller-Rabin. And we'll show you some powerful power of randomness. Interesting. And if time allows, I want to tell you maybe about, again, quickly polynomial identity testing. But this is going to be definitely if a time allows thing. And there are more things I could do depending on how much time we have. Like in replacing with PIT as well. I might not do PIT, I might do something else depending on how much time we have. But the broad goal is to at least look at the first one in good detail, understand what's going on. Miller-Rabin will spend some less, possibly less time on. And if we still have time remaining, I'll show you some other things. Does that sound good? Okay, good. So the min cut problem. So the problem is given a graph G, find a min cut, i.e. find a set S such that the number of edges going from S to S bar is minimized. And S is not V and S is not empty. So it shouldn't be the entire set, it shouldn't be the empty set. But beyond that, it is okay. Does the problem make sense? So you have some graph. This is your graph. You want to find some set of nodes, a subset of nodes, such that the number of edges going across is minimized. So for here, like one such set is just this node separated because only one edge goes across. So that's a min cut in this case. Now, if we replace this, now every edge has at least two edges going across. So still, this sort of a structure is a min cut. But for example, if I have this kind of a thing, then there is a min cut which is of size 1, but there's no single node which is a min cut because every node has degree more than 1. Does that make sense? So
Can
you
you repeat
want to find
what a min-cut
these.
is?
What?
Can you repeat what a min-cut is?
Min cut is just the smallest set, a set such that the number of edges going across it is minimized.
What
You
do you
can
mean
think,
going across it? Listen.
so if I divide the graph into parts like this is S, this is S bar, then there's only one edge going across.
Okay, okay, makes sense. Yeah,
The other way you can think of it is what is the minimum number of edges you need to remove from the graph so that it's disconnected.
yeah, that makes sense.
Because then it will correspond to the connected components afterwards. Like S will just be one of the connected components afterwards, and that will be how you separate out into two components. Is the problem statement clear to everyone? What a min cut is?
Yes.
Good. So the problem is given a graph G, find a min cut efficiently. And I don't want to get into what efficiently means too much, but the point is you should really not be taking as like going over all sets, for example. Your algorithm should do something smart, you should be somewhat fast.
I mean, whenever I hear like I need to cut the minimum number of edges to get a disconnected graph, I think of a tree. So if we are given a graph and we go to its spanning tree and then do this, won't it work?
I mean, in a in a tree, your min cut is always one of
Yeah.
size one, like for example, a leaf. But here we know that there is no cut of size, like
Yeah, no,
just
but
a.
yeah, but we are going to the spanning tree of the graph.
I'm giving you a graph. You can't change the graph. You can do something by looking at the spanning tree, but I want you to find the min cut of the graph that I gave you. I'm not saying that, oh, is there an algorithm to find a min cut of some graph? For trees, it's easy. Like you can imagine, like you have like huge cliques, like I don't know, K 100, two edges going across a K 100 as well. Okay. Even here, the min cut is of size 2 because size 2 because I can just divide the graph like this. But like there is no min cut which is of size less than 100, let's say, or of size 1. Okay. Sorry, there's no vertex set that I can cut which is of size less than 100, and there is no min cut of size 1.
Can you explain what is K100?
Oh, I'm sorry. A K100 is just a like I just meant like Kn is a fully connected graph on n vertices.
And what does connecting the graph with edges mean? Like you connected two graphs with edges.
There are nodes inside, right? Just pick some nodes inside.
Okay.
I just wanted to say that there are like cases which look very far from a tree. Like here, I just put two, but you could imagine even if I put like 30 things here, 30 edges going this way, 30 edges going this way, 30 edges going this way. The min cut is still of size 60. The min cut is now of size 60, certainly. Yeah, good. Okay, so how would we approach this?
Like I have very less idea, but like here in this example, the K100 is very like clustered, but and this K100s are very clustered. It's like fully connected. But we can just look at some place where there are a lot of a local place where there are a lot of edges and try to do something like that's what I was thinking because or we can just look at some cycles and try to disconnect them. Like yeah.
Yeah, so there's lots of things you can try. And like some of these do actually work, like you can actually do them. But it's very hard to make all of this work. So Karga comes in and says this ridiculous thing. Karga says, don't be smart. Don't try to do all these things. Do the following. One, pick a random edge, uniformly random edge. And contract it. So I'll tell you what a contraction is and contract it. Two vertices remain at the end, that's your cut.
By the way, is the graph simple or like any graph works?
Even multigraphs will work, but first we'll assume simple for today.
Oh.
Okay, so ridiculous sounding algorithm for anyone who knows what a contraction is. But let's take this graph and we'll try to see what happens. Good. So you start with this. So there are how many edges? 1, 2, 3, 4, 5. Okay, let me name vertices v1, v2, 3, 4. Okay, so can pick a random edge. Okay, I need to call on someone and they need to pick a random edge. Does somebody want to pick a random edge?
V5, V6.
V6, V8.
V6, V8. Okay, good. So I know this is not very random. So don't shout at me if somebody is like, this is clearly not a random process. Okay, good. So what we do now is we want to contract V6, V8. What does that mean? We'll make V6 and V8 into one single vertex, which I'll now call V6, 8. The rest will stay the same. So V1, V2, V3, V4, okay, let me move this somewhere. V5, V6, 8, V7. So all the other edges remain the same. Sorry, I had this cycle, then I had V3 going to V4. V4 had an edge to V6, 8, so that remains. So now the thing is V8 had a no edge to V7 and to V6, right? But V6 also had an edge to V7. So I'll now have two edges from V6, 8 to V7. Okay. So this is my graph now. So what it's kind of saying is imagine the graph if you know that if you had already decided that V6 and V8 are going to be in the same side of the cut at the end. So this is just saying like you pick a random edge and you take its two endpoints and decide that they are going to be in the same half at the end. If you knew they were in the same half, then this is kind of the remaining graph because you can treat them both together in one place. Okay, a different person, pick a random edge.
V4, V5.
V4, V5. So we do the same thing again. Let me try to see if I can do this more efficiently this time. This becomes V4, 5. And there is a second edge going from here to here. Somebody else?
V1, V2.
V1, V2. Good. Somebody else?
Can I do V45 and V68?
Yeah, sure. So now we'll be careful and see how things work because we are merging something more complicated, but nothing crazy should happen. So we are merging V45 and V68. So this becomes V45, 68. This vertex goes away, and there were two edges here, so that just comes here. Does everyone see how this happened? The edges between V45 and V68 disappear, the rest add up. One more person, only two more steps remaining. So come on, somebody pick an edge.
V1, 2, and V3.
V1, 2, and V3. Great. So this becomes V1, 2, 3. And observe that there's only one edge going here, so that remains, and this all disappears. Okay, finally, somebody pick an edge.
Can
Unif
can
the
we
edges.
contract V4, 5, 6, 8, and V7?
Oh wow, you all are like the nicest people ever. All of you decided not to make my algorithm work in the first go. It's incredible. Even randomness is not so kind. So this will be for 5, 6, 7, 8. So now there are some vertices in this on this node, some vertices on this node. We declare that this is the cut. So V1, 2, 3 and is one side of the cut. V4, 5, 6, 7, 8 is the other side of the cut.
Okay, that's the cut. Okay, how did this happen?
So we just go back and say, oh, you divide 1, 2, 3 in one half and 4, 5, 6, 7, 8 in the other half.
Yeah, how
That's
did that happen? This is magic.
So it worked because, like, okay, it should not work in one go. You all were too nice. You all avoided picking this edge. If any of you had picked this edge at any point, of course, this would have gone. This would have not worked, right? If
Oh,
any
which
of you had V3, V4, this doesn't work, right? But,
right, we didn't pick V3 and V45. Right, right.
but the thing is, I want to say that it's not that likely that any of you pick this edge. So let's try to understand this. So does everyone see what the algorithm is? Does everyone understand how the algorithm works?
Yeah.
Great.
Yeah.
Okay, very good. So I'm so excited right now. This worked. Like you all were so nice and didn't pick that edge. Okay, cool. Uh,
I don't
okay.
understand what did we get from the algorithm.
So we divided the vertices into two halves. We were able to get a way of dividing the vertices into two halves. We do this thing of contracting edges till we have only two vertices remaining. And we say these are the two halves, like S and S bar.
Oh,
And
okay.
go across it, we'll declare that to be the cut that we care about.
But
And
we know that the number of edges between these two are minimized.
that's what we want, yeah.
But
Wait,
how do we know the
if
minimized?
if we did pick V3 and V45, like it won't work at all. Like,
It won't work. It wouldn't have worked. But I want to say that the probability of you doing that is not that high. It's like, right? Like we ran it for like 6 steps. So it's of course like at least 1/6 that you would pick it, roughly. That's not true. That's not true. But like roughly it's at least that much.
So,
Does that make sense?
what do we do if it fails? And how do we know if it fails?
So one thing you could do is if the probability is not too small of it working, you can run it 1,000 times, this simple process, and see what's the min cut you get across all these 1,000 attempts. And if the probability it was not too small, you'll find this in like at least one of those 1,000 attempts. And then you can just use the one which was the minimum across all your attempts and claim that that would work. That's good enough. Does that make sense?
Yes, thank you.
Good. So now let's understand why this worked or why would this work. So say G has a min cut of size C. Okay. So one thing you should note is that in this process, the size of the min cut can never reduce because we are only merging vertices. So we are only saying that these are together now.
What is the size of a min cut?
The number of edges going across. The size is this quantity. The minimum across all sets of the edges going from S to S bar. Observe that like if we look at any point, let's say here, and we say V4, 5, V1, 2, 3, 4, 5, then the number of edges going across this cut, across these 3 nodes and these 2 nodes, is exactly the number of edges going across from all the 5 nodes and those 2 nodes, and all those 3 nodes. Does that make sense? Like, because the only edges that have been removed are internally in this part. So this process never reduces the size of the min cut.
Wait, it never increases or never reduces. It remains some invariant, the size of the min cut.
It can definitely increase because like it could have contracted V345 and that increases the size of the min cut. I'm just saying it cannot decrease. So say G has a min cut of size C. Okay. Can you say in one step of this process, what is the probability of picking this edge? Like one of these C edges to contract on. If you don't contract on any of these C edges, you're happy, right? In that step. So what is the probability of contracting on one of these C edges?
1 by C.
No, you picked a random edge from all the edges in the graph.
C by N.
E by number of edges at that step.
Good. C by number of edges. Right? And do you know how large the number of edges is? Can you at least lower bound it? You know the min cut is size C.
3 into VC2, where V is the number of vertices.
Good. So if the min cut is size C, then every node has degree C, at least. Because like you could have just separated that node out. So there are at least NC by 2 edges, which is less than equal to 2C over N. Sorry, 2 over N. So actually picking a min cut edge is not that likely in a given step. If
And is
there
the
are
number of vertices.
N is the number of vertices at this point, yeah. So let me just say 2 by V.
So is it like if you avoid min cut edges till the very end, you will
Yeah,
up with it? Is that the logic?
exactly. So you start in the first step. You fail with probability. You succeed with probability 1 minus 2 by N at least. Right? And now you have N minus 1 vertices remaining. You succeed in this step as well with probability 1 minus 2 by n minus 1. And then you succeed in the next step as well with probability at least 1 minus 2 by n minus 2. And all the way up to at least probability 1 over 3. Does that make sense? Sorry,
Yeah.
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 2 over 3? 2 over 3. Right?
No, you have 1 minus 2 over 3, right? So,
1. Right.
Good, good, good. So what is this quantity? So this is n minus 2 over n times n minus 3 over n minus 1 times 4 over n minus 2, 1 over 3. Does anyone see anything nice happening in this product?
yeah,
The numerators are cancelling out to get 1 over, 1 over n times n minus 2.
yeah.
So it's just 1 times 2 times n minus 1. So this algorithm, this ridiculous thing of just picking a random edge and contracting it works with probability roughly 2 by n square. Okay. So I can just run this whole algorithm n square times. And this algorithm is easy to run. It takes nothing, right? Pick a random edge, contract it.
Yeah, but isn't
Like,
contracting a little inefficient? You have to decide which edge.
right? Because you just merge them. But okay, there are efficient ways of implementing contracting. There are better ways of doing this as well. I don't want to talk about that too much. But the lesson here is, let's say even if it takes like, I don't know, poly n time, this whole thing you can repeat it n square times roughly. So just like running in poly n time, like some n to the constant amount of time, I can find the min cut using this approach as well. Like that's what I want to convey to you. Like I'm really not going over everything. Like going over everything is like 2 to the n time. It's exponential. I'm only doing like poly n times. And I'm still working. I'm still finding the min cut. So that is the ridiculousness of Karkir's algorithm.
Is this the best? Like, is it O square the best we can do for this problem?
Uh, I mean, for finding them, like the probability of finding the min cut, is that what you're saying?
No, for finding min cuts in general.
I mean, there like you have much faster algorithms which also work deterministically.
Oh,
Like now we do, but like the point is not that, right? The point is, of course, that there are better things you can do in this case. Like here, like it's not offering necessarily a speed up. It's just like a nice algorithm. There is one thing that it does, which is actually very cool. So you can note that this is not just the probability of finding a min cut of size C. It's the probability of finding any given min cut of size C. Like you could have decided what the edges you care about are in advance, and it will still work with the same probability of finding that exact min cut. Since any given min cut has this much probability of being found, there can be at most n choose 2 min cuts.
What do you mean by given min cut? Why
Like you
would
could
it?
have a way of partitioning, which is a min cut. Like you could have decided that this set S and this set S bar is what I want at the end.
Okay, okay.
which minimize the number of edges going across. I'm saying there are only n choose 2 ways of picking these two sets,
Yeah.
which minimize the number of edges going across.
Can you
And this is
please
not,
repeat your last statement?
I'm just, okay. So this is, I know this is a bit trickier. So I'm saying that for any given min cut, there's a probability 1 over n choose 2 of finding it by this algorithm. At least, right? There's
Yes.
a 1 over n choose 2
No,
of
like
finding it.
it's the probability of not finding it.
The probability of finding it. This is the probability of finding it. This was the probability of succeeding in the first step and succeeding in the second step and succeeding in the third step and succeeding in every step. It's
Yeah.
the probability of. So there's a 1 over n choose 2 probability of finding any given min cut. But that means that there can be at most n choose 2 given min cuts anyway, because like each of them has a probability. Each min cut has a probability of 1 over n choose 2 of being found. And you can't find more than one by running this algorithm once. And this is tight. You can't actually do this because you can consider the cycle on n vertices. So the min cut is of size 2, and any n choose 2 pairs of edges will form a min cut. Removing any two edges disconnects the graph. So this is actually tight. So this is one incredible thing that comes out from this algorithm. Does that make sense?
Yeah.
Yeah.
So it's not a priori obvious that there should be like polynomial even like min cuts, right? Like it could very well be that there are many, many different ways of constructing min cuts, and this shows that no. Not only can I find a given min cut with like good probability, all of like there are not too many of them because I can find any given one with good probability. Does that make sense? Okay, so how are we doing on time? We have another 45 minutes, right? Okay, so if you followed this, uh, so maybe I'll wait for 1 or 2 minutes. I'll wait if you have questions, I'll take questions. And then we'll completely switch gears. So even if you didn't follow this, it's completely fine. You can like restart and like we'll do a completely new problem. So if you have, you can ask questions on
Can you
everything.
just briefly repeat how there are at most n choose 2 min cuts?
So I'm saying this, say S is a min cut of size C, then this is the probability of finding C, finding S. Okay.
Yeah.
I'm saying any given, for every set S which forms a min cut, this is the success probability.
Yeah.
But I only found one thing at the end, right? I can only find one of them at the end.
Yes, yes, correct.
So there cannot be more than n choose 2 different ways of finding things, because at least one of them, that means does not get found with probability 1 over n choose 2.
Right.
I know this is a bit trickier, but that's why I didn't want to get into it. But
I mean, like the success of finding one of them is 1 over n choose 2. So you're saying that therefore there will be at most n choose 2 min cuts.
exactly.
Okay.
Okay, any other questions before we switch to the next part? Okay, if you have friends who left, who got tired of this, maybe try to invite them back.
I have a question like this might be unrelated, but how do computers which are deterministic produce random results?
What do you mean? Sorry, I didn't follow the last sentence.
How do computers produce random things?
How do computers produce random things? It's a much trickier question. uh, um, so the computers cannot produce truly random things, of course. Uh, so they produce something that looks random. They'll take a bunch of different variables which are supposed to be random, and they'll just combine them in weird ways and hope that whatever it comes out at the end looks random.
I was told that computers consider the date and time before chooses random things.
That is, you can just throw in any number of factors, right? Like if you and then you merge them in weird ways and no, there is a definition for random. What do you mean? Because what do you mean there isn't a definition for random?
Like, I
No, I
mean,
mean,
decide whether a number is random or not. Like, there's no formal definition.
There is.
Oh,
You can definitely define all these things. Like what computers produce are called pseudo-random bits. They're not truly random. And the whole point is that no efficient algorithm should be able to differentiate between pseudo-random and truly random bits. And if your algorithm cannot differentiate between pseudo-random and truly random bits, then it will just work because it worked for random bits. Because if it didn't work for pseudo-random bits, that's a way of differentiating whether the bits were actually pseudo-random or random. Yeah, that's not a question I want to talk about now, but these are all things that can be well defined. Good.
and for this thing, for in this slide, like there are NC2 edges at most, right? So at most there can be at most all can be min cuts. I mean NC2 pairs of vertices. So at most each pair of vertices can have a min cut. So can't we say by this method also that there are at most NC2 min cuts?
There are, no, by this method you said because any subset of edges could be a min cut. So by this method you would say something much worse. You would say 2 to the n choose 2. 2 to the n choose 2. Like it is slightly sillier bound, which is just 2 to the n by just dividing the number of sets s. But like the min cut size could be much larger. As I said, here the min cut size is like 60. If I have like 30 edges in each way.
Yeah, I got it.
Yeah. How did someone come up with this type of algorithm? I don't know. I really don't know. It's ridiculous. Uh, good. All right. So let's look at the second thing that I want to talk about, which is Miller-Rabin primality testing. So the question is, I give you a number n, given positive integer n, check if it is prime. So one thing to note is, of course, it is easy to do this if you run in time polynomial in n. And you might have seen ways of doing this if you run in time almost root n, right? What I want you to do is run in time polynomial in log n. So polynomial in the number of bits taken to write the number, because my input is not actually the whole number. My input is just the number of, like the size of my input is just the number of digits taken to write n. Okay, so this is the task. Given positive integer, check if it is a prime. ideas people.
Check for all numbers till square root n.
That's too long. There are square root n numbers. I don't allow you that much time.
We can also consider the remainder by 6
Okay.
because
If
every prime is of the form like 6k plus minus 1. So it should remove some cases.
remove some cases, yes. What do you do? Like there are like still like you're still left with a third of all the numbers.
I mean, still like for the square root n thing, you can just check all the primes till square root n. You don't have to check all the numbers.
Yeah, I was trying to say.
That is also still roughly square root n. There are like square root n over log n, many primes.
Square root, acha, right. You just want log n.
I just want like polynomial in log n. Like log n to the 100 I'm fine with. Log
Okay.
given positive integer n, check if it is a prime. Mod n, every residue class should be probability 1 by n. Sure.
I mean, you also have the modular thing like prime minus 1 factorial is congruent to minus 1 mod 2.
That's a
That
good observation. Yeah.
that's only for
No, but that's
primes.
like a necessary condition, not a sufficient one.
That's a
Good.
sufficient condition, isn't it?
Listen.
That happens only if the number is prime.
You're
Yeah, but
saying that
no, but if it no, sorry, that's a sufficient, but like not necessary. No, sorry, it's wait.
If it is sufficient, it is necessary.
you're saying p divides p minus 1 factorial plus 1.
Yes.
No, like sorry. Uh, if it's prime, then p minus sorry. Hold up.
I mean, it's like the Wilson's formula. Wilson's formula works only if and only if the number is prime.
You're saying, yeah, the problem is Wilson's is too long. It's like n, it's like you have to do n multiplications. Wilson's will work.
Oh, okay.
Wait,
So
it's
confused with
n
Fermat's
multiplication.
theorem.
Is
Yeah.
isn't one operation like O of 1? So you get O
Yeah.
of n here.
Yeah, that's too much. I only want like polynomial in number of digits. Again, like otherwise, like the division technique already worked, right?
Yeah.
Okay, but you're thinking of good things. You're thinking of identities that you know about primes. So you know Wilson's. What's the other one that you know?
Fermat's, but then that's again, sorry, like yeah, by necessary and sufficient, I was saying Fermat's. If it is prime, then it will fit that. But if
But you have
Good,
Carmichael, so
for
like
prime, then
very good. But that's a starting. So it's a starting point. You're saying pick a number n, pick a number a, number, let's
Can
say,
we check the quadratic residues mod n?
how do you check that?
No, if the number leaves the remainder 1 or minus 1,
Okay.
uh, like then like say if n is a prime, then x square is congruent to 1 mod n. Then n should be either 1 congruent to 1 mod n or x should be congruent to n minus 1 mod n.
Okay.
Then I mean it should help in such some way.
there are a few other necessary but not sufficient checks, such as it being 6k plus or minus 1, other than 2 and 3, of
I
course.
mean, I mean, format
If it
is also
doesn't
not
fit,
sufficient.
you would eliminate, but if it
Yeah,
fits, you still continue to do other checks.
even format is not sufficient.
Yeah, exactly. Even format is not sufficient, but it's necessary.
Yeah, so you don't need necessary. You need just sufficient because you have very less. Log n is very less.
Yeah, but then if you have sufficient, you might miss out on some primes because it's not necessary. But when you're calculating like time complexity, how much you cut down doesn't matter because you take the worst case.
It's fine. Like if you reduce cases and if you were able to somehow reduce in only order log n cases, that would still be useful. It's just that this technique you don't even have a way of reducing. in like by half, if you were able to reduce each time, that's good enough.
Yeah, for example, the 6k plus or minus 1 reduces like
To a
maybe
third of the cases, it's
66%.
not bad, but it's just like
Yeah.
not enough because we don't know how to build on top of that. Like it's just one check. Like it does not
Yes.
actually.
So we need to look for identity which has halves, which includes halving the numbers somehow.
It's okay.
Since we are discussing random algorithms, I think we should try something random.
Okay, good. Very good ideas. Can I finish writing Fermat's little theorem, please?
Yeah.
So pick a number is -1 is congruent to 0 mod n. Successful for primes. So one way of choosing randomness is just picking in this choice of alpha, by the way. Successful for primes. So that is happy, but also successful for some special cases. Successful for, as somebody said, Carmichael numbers.
Though I don't think there's too many of them that come frequently. So
That's true.
this should work to a good extent.
What's a Carmichael number?
I mean, it works for every primitive root, right? This format FLT.
No, I mean, this is true always. What are you talking about?
What?
This statement is true for all alpha which are non-zero modern.
No. I mean, it also works. I'm talking about it also works for all primitive roots, I think, or something like that. Like it works for primes, this thing. If you choose an alpha, you get this works for primes. It also works from like this Carmichael's and also some of the primitive roots that has n minus one as
Okay,
modulo.
okay. You're confused about the definition. You should. It's okay. Maybe just, don't worry. I think the numbers which fail this test are exactly the Carmichael numbers. I think you can just look it up. Right? Carmichael numbers are exactly defined to be the numbers that fool this test. So
Oh, okay.
So how do we plan to compute the n-1 power of the number?
good. So because I just need to do it mod n, right? Let's look at if I have 2, I want to compute 2 to the, can somebody say largest number, which is not too large? Like I can think about it, but
543.
543, my God.
Okay, too
So
large maybe.
too large.
54.
100,
Remove
100,
one.
100.
100. See, this is the kind of behavior I want, like exceptional. So I want like 2 to the 99 mod 100. How do
Wait,
I do
like
it?
if too easy. Okay, wow.
Yeah, you would
Right.
just yeah.
2 to the 49 square, right? Mod 100. So I can try to compute this now. So this is 2 into 2 square into to the 24 to the 400. This is 2 to the square, 2 to the, let's say, 6 to the 16, 100. So now I can just start removing this. This is 8. This is 64 to the 16, 100. And I can reduce the 64 to the 16 is uh, 96 to the 8, 16 to the 4, 56 to the 2, 36, just 28. So it's like 28 mod 100. So the whole point is you can do exponentiation, like you can square every time.
So this works in log n, right? So that's
It works in
in log n time, so it's okay, right?
Exactly. It works in like polylog in time because I can just make the binary representation of the number n and compute each power separately and then just multiply them all together. And since everything I'm doing is mod n, I'm never exceeding like log n digits. It's like the number of digits is always preserved because the point is like I wrote 64 and then I wrote 96. I did not write 4096.
Yeah, so we got for polylogin. So but we also have for like those Carmichael numbers. We have to remove them.
Exactly. How do we do that?
And we have to do that in polylogin again.
Again, good. Somebody had a very nice idea. Oh, polynomial in log n. Polylog n is just polynomial in log n. Like, yeah, log n, log square n, log cube n, as long as the amount I'm putting on top is a constant, it's polylog n. Good, but somebody had this nice idea earlier, which is so let's think of like alpha. Uh, if this was a prime, right? Let's say if n was a prime, then half of the numbers have the property that alpha to the n minus 1 by 2 is minus 1, and half of the numbers have property that it's plus 1. Uh, is that true? Does everyone agree?
Yeah.
Would you mind repeating?
I said alpha to the n minus 1 by 2 is plus 1 for half of possible alphas, and minus 1 for half of possible alphas.
Right, yes. So you can kind of do the opposite of this thing, multiply it by a power of 2, something like
What do
that. Uh,
what do you mean by that?
I was thinking by going backwards a bit.
Yeah, what do you mean by going backwards?
Okay, I'm not really sure if that will work because it's a bit different. It's n minus 1, not n.
Okay, so one way of checking is just to check at this point if like a given number goes to plus or minus 1 if you raise it to the n minus 1 by 2th power, right? That is one way of checking. But the problem is there are actually Carmichael numbers which even satisfy this test. That like the alpha to the n minus 1 by 2 is always plus 1 or minus 1. For
But are there more Carmichaels which then when you don't do this thing, or are there less?
oh, I mean,
Should we?
not all Carmichael numbers have this property. That's true.
So
We
this should
can
be better.
do
This method.
Doing both, like you can do both checks, right? Two checks is completely fine.
Do the first check. If it works, do the second check.
Good.
Thank you.
But we're somehow a bit stuck, right? Like we are still running into the same type of issue. But what if I keep
Do this
going?
again. Yeah. Do this again.
we can do something like
This
do
was
this
divisible.
test several times.
4, yeah.
Like assume n minus 1 has v2 of something r, then we can
Good.
run this test r many times.
Good. So if let's say
That
n
is this
minus
one.
is q times 2 to the r, I can find this efficiently just because I can keep dividing by 2 till I hit an odd number, right? And if it's given in binary, it's even easier. Just find the smallest one, and the rest is your thing. Good. So n minus 1 is q times 2 to the r. What you do is you compute alpha to the q. Okay? You compute alpha to the q. You see if this is plus or minus 1. Okay? You then compute alpha to the 2q. This is plus or minus 1. Like if it was not already plus or minus 1, did it become plus or minus 1? And you keep going till you hit alpha to the n minus 1. Okay? And now you must have hit plus 1. Okay? The point is, at some point, you switched from minus 1 to a plus 1. Like before that, there were some other numbers, and suddenly you must have hit a minus 1 and then a plus 1. Does that make sense? Because the square root of a plus 1, like it could also just be that you hit a plus 1 here itself. Then there's nothing to do, right? But the only square roots of a plus 1 is a minus 1 mod n, right? Does that make sense? Mod n, the only square root of plus 1 is minus 1 other than 1 itself. But that's not true for other things. That's not true when it's not a prime. For example, if it was
What's not true if not a prime?
like if n is a power of a prime, then this is still true. But if n was not a power of a prime, then there are square roots of 1 which are not minus 1.
Oh,
Half of them, at least half of them, are not minus 1. So let's say if n was p times q, where p and q are coprime. Okay, I already used, let's say, a times p. A comma b.
While computing each power of alpha, why must you always get plus or minus 1 and not any other?
I'm saying you'll start with something which is not plus or minus 1. You'll eventually hit a minus 1 and then you'll hit a plus 1 if it was a prime.
Yeah.
You know that you hit plus 1 eventually, and the thing before a plus 1 must have been a minus 1.
Okay, yeah.
You're squaring every time. So n is AB with GCD of A comma B is 1. Right?
so you mean if it's not a prime, it can be like it is some number and you square it suddenly becomes 1 instead of becoming a minus 1.
Exactly. Exactly.
Okay,
So
and
for example,
that does not happen for primes.
exactly. So in particular, the number which is plus 1 mod A minus 1 mod B.
Can you give like an example of alpha and q?
Okay, we'll try running this, but let's try running this. Let me finish this thought and I can give an example.
Yeah.
So let's consider n is AB and consider the number which is plus 1 mod A minus 1 mod B. There exists such a number, right?
Yes, by
So
CRT.
by CRT. So when you square this number, you get 1 mod AB because the resulting number is 1 mod A and 1 mod B. Similarly, you could have done like any combination of pluses and minuses, and all squares will. So there are two possibilities in this place when you consider the graph, which is like what gets you to 1. Two possibilities which are not plus minus 1, and two possibilities which are plus 1 minus 1. And you can actually check that with probability half, you will go through one of these if you pick a random alpha. If you pick a random alpha with probability half, you'll go through one of these square roots when you hit 1.
Yeah.
So what's the algorithm? Just do this. Just start with a random alpha, keep squaring it till you hit 1. Check if the number you went through is plus or minus 1 or not. If it's not, done. And you can
What
repeat this and success probability.
what if alpha par q, alpha par 2q, and everything are plus minus 1 mod n, but n is not a prime? Why can't that not?
So this is unlikely. There are not too many alphas that would succeed in doing this.
You
Ever.
mean too many n's, right?
No, for any given n is what I'm checking.
Yeah, but how are you sure that all Carmichael numbers will have square root of 1 as not minus 1?
That's what I said. Any composite number which is not a power of a prime does have this property.
Okay, and if you are choosing a power of a prime,
That I can just check.
okay.
I can check if a number is a power of a prime. It's a power of some other number. That's easy to check. Like you just need to check if it's a log n up to a log n power, right? You can just check if it's a square or something. You can check if it's a cube or something. There are smarter things also that you can do, but that's an easy check.
But how is this running in polymorgan time? Because you're essentially randomly checking for alphas, but what if the number is actually prime? So you have to go through each alpha, right?
No, I'm saying I'm succeeding with high probability. I'm not surely knowing. I'm just succeeding with high probability. In a random alpha, I succeed with probability half. So I only need to check a very few alphas to be very confident.
Okay.
Yeah. So this is Miller-Rabin primality testing. Okay, so we have about uh, 10 minutes more. So maybe what is the best thing to do? I'll tell you what polynomial identity testing is, and I'll probably not be able to get into applications, but what is polynomial identity testing? This is very easy. This is a very easy application. So how sometimes you define polynomials is because like if it's a very long polynomial, like writing the whole polynomial down can be somewhat inefficient, right? For example, if you consider the polynomial which is like 1 plus x1, 1 plus x2, 1 plus xn, and this is a polynomial in n variables, writing this down has like 2 to the n complexity, right? Just because each
Yeah.
thing will take. It's like very simple polynomial. It's like only n things, right? So sometimes what you want to do is not represent your polynomials by just writing them out. Sometimes what we do is like you say that, oh, I'll give you a circuit which takes in like 1 and like your inputs as x1, x2, xn, and tells you how to add or multiply them. Like for example, this is a very small circuit which computes this polynomial. It says this gate takes its inputs, which are 1 and x1, adds them. This gate takes its input, which are 1 and x2, adds them. And all of these do these, and then you multiply. That's a very small circuit. Okay. Now the problem is, I give you a small circuit. Okay. Check if the polynomial it's computing is exactly the zero polynomial.
What is a circuit here exactly?
It's just like some and like sorry, addition and multiplication gates.
Okay.
And your inputs are like variables. And your
Yeah,
like
okay.
given
We are giving this. What are we expected to do?
Check if the given circuit evaluates to the constant zero polynomial. So you can think of it's also, I can ask you if like two circuits are equivalent, and that's the same because I can just add another gate which is subtract these two and check if it is now the zero polynomial, right? So it's a more general problem, but okay. Can you check if it's the zero polynomial? Okay. Here's the great idea algorithm. Pick x1, xn randomly, evaluate the circuit. The whole point is a polynomial does not have too many roots. So if you pick these points randomly, it's probably going to be non-zero if it was a non-zero polynomial.
Yeah.
And that just works. That's it.
Wait, I didn't understand.
Yeah, what's the question?
Hold on, let me just check it again.
Okay, so I'll maybe make some comments while you think about this. So one interesting thing is we know how to do the first two things that I mentioned without using randomness as well now. We know how to do min cuts without randomness. We even know how to do primality testing without randomness in
Wait, what is
polylogging.
like what is randomness? Because in Mincuts we are choosing a random edge.
We have another algorithm, a different algorithm for solving the same problem, which does not use randomness, is what I'm saying. Like as a community, as computer scientists and mathematicians, we know other ways of finding min cuts which do not use randomness and are very fast.
Okay.
We also know now, like in the past 20 years, we know how to do primality testing
Without
without
using a random alpha?
without using randomness at all.
Does that mean the algorithm is like completely sure?
Exactly, yeah. So we know how to do this, and this is like a very huge paper. Like this was primality testing was by Agrawal, Kayal, and Saxena, and they won like all kinds of prizes. It was a huge result. Uh, the thing is, we don't know how to do polynomial identity testing without randomness. This is basically the only way we know how to do it. Pick random things, evaluate and check if it is non-zero.
Like, why would you even need to do things without randomness if randomness is okay?
It's just, so, I mean, you could be okay with randomness and you're glad. One thing is you don't trust your source of randomness because we don't have truly random things actually. One thing is you want to be sure. You don't want something which is not definite. The other is, I don't know, it's just interesting. Like, uh, is there a fast algorithm that does this that does not use coin tosses? We don't know.
I mean, like, isn't getting an algorithm working properly and the algorithm just using coin tosses more fun? Like you're doing random things and you're getting something.
Sure, it's more fun. But like the question still remains. For primality testing, by the way, if anybody actually does primality testing in practice, which they do, they use this algorithm roughly. They don't use the deterministic one because this is much faster.
What does a deterministic one use? Like which identity? This one only, FLT only.
It's more complicated.
Okay.
But we can't be sure here for using this algorithm. We can't be sure that it's a prime or not. Like most probably it will, but
I guess we can be sure if it's not a prime, right? So In practice, if you can just double check it with the deterministic algorithm if we
No,
are getting a prime.
I mean, sorry, what does that mean? If it, so what you're saying is, if it's a prime, it will always succeed the test. If it's not a prime, it will probably fail the test, right? So, but we
Yes.
are still not sure if a given number is a prime but the thing is, if you run this 1,000 times and you're confident with probability like 1/2 to the 1,000, are you really not sure? Like that's more than whatever people's like how like number of atoms in the universe or whatever, right? Like there are much like your computer failing is like your computer not working properly is more likely than that.
Yeah, makes sense.
Like a random bit flip happening in your computer is much more likely than that. So yeah, but it's an interesting question, like regardless. Yeah, whatever, right? Like I don't know. Like I don't know. Yeah, there are much unlikely, like much likelier things that can happen before this algorithm fails if you run it enough times. Yeah, very likely. Why would you say something like that? Like, be confident. You'll do fine. Yeah. Anyway, uh, yeah. So I think I'll stop here. But again, the only reason I wanted to tell you about polynomial identity testing is one, such a ridiculously simple idea, and secondly, solve it deterministically. Everyone will be very happy. You'll be the I don't know. You'll get many prizes.
Just
But as
to